increasing greenhouse gaseous emissions mainly contributed by the carbon dioxide that was generated from the combustion of fossil fuel and natural resources. This situation had impacted the environment, causing global warming and climate change. Carbon capture storage, CCS, is regarded as one of the strategic solutions for mitigating climate change. The CO2 has been collected without being used, it is compressed and transported for use in different applications via pipelines, ships, trains, or trucks. Alternatively, it can be injected into deep geological formations like saline formations or gas reservoirs, which trap CO2 for long-term storage. Among the CCS technologies, adsorption capture is one of the most widely used methods for separating mixed gases worldwide. Carbon dioxide has two oxygen atoms bonded to a central carbon atom through a covalent double bond. The electrostatic potential surfaces of CO2, illustrating the distribution of charges on the molecular surface. The surfaces plotted in pink indicate the negative potential regions, while the surface in green indicates the most positive region. The surface potential site of CO2 shows the carbon atom with a positive charge due to the poor electron density, as the oxygen atoms at both ends are known as high electronegative atoms pull the electron density towards themselves. Thus, different potentials of the positive and negative regions can later form electrostatic interactions with electrophilic and nucleophilic areas in other molecules. Nitrogen-rich porous solid adsorbents have been widely explored for their CO2 chemisorption ability under low CO2 concentrations. Functionalizing solid adsorbent using an amine-impregnated CO2 sorbent system has received considerable attention to enhance the performance of non-tailored adsorbent materials. Nitrogen-rich functional monomers such as methacrylamide, allothiorea, vinylimidazole, and acrylamide are commonly considered in preparing the polymer adsorbent due to the basicity of the nitrogen-rich functional group having an affinity towards the acidic CO2 gas. Adsorption refers to the process wherein CO2 molecules adhere to the surface of a solid adsorbent, which possesses residual surface energy owing to imbalanced forces. The practical adsorption technology with solid materials has the potential for the adsorption of CO2. With its controlled waste generation, high CO2 adsorption uptake under ambient settings, high specific surface area, high mechanical durability, appropriate pore size distribution, and accessibility for regeneration, adsorption offers minimal energy requirements and low operating costs. Desirable criteria for an ideal adsorbent include CO2 adsorption capacity, CO2 selectivity, adsorption kinetics, ease of regeneration, stability under repeated adsorption-desorption cycles, sorbent cost, synthesis process and thermal stability. The surface molecular imprinted technique, SMIT, has better separation efficiency and rapid binding sites. By applying the lock and key concept, this customized polymer could obtain selective properties. The polymer complex, which consists of the target molecule, functional monomer, functional crosslinker, solvent, and initiator, is beneficial when the target molecule is removed from the polymer. This process leaves a cavity with a complementary shape, which increases selectivity. The MIP was synthesized by dissolving all component molecules with continuous stirring, followed by purging with CO2 gas to allow the self-assembly between the complex. After adding around an initiator, the mixture was sonicated to achieve homogeneity. After that, the homogeneous solution was kept in an oil bath at 60 degrees Celsius while constantly stirring to promote polymerization. Once the reaction was stopped, the polymer was filtered and centrifuged to eliminate any remaining reagents. A fixed bed column was used to perform the carbon dioxide adsorption experiment. The functional groups of the material were determined using FTIR by analyzing the spectrum. The surface morphology of the polymers can be analyzed using SEM at different magnification. Therefore, the characterization analysis proved that the polymer was successfully prepared through the surface imprinting technique. The CO2 adsorption capacity of MIP fluctuated by an average of 4.2% during 5 consecutive cycles, indicating that the adsorption performance of the developed sorbent was relatively stable. Overall, our results indicate that the GMIP adsorbent was successfully prepared using the reported procedure and demonstrates strong potential for carbon dioxide separation in fixed bed columns. This composite material shows promise for reliable and effective carbon dioxide capture in practical applications. A cost production of GMIP is comparable with the available commercial polyethylenamine, PE, thus indicate that GMIP has a promising potential as adsorbent for CO2 adsorption, as GMIP has better selectivity and molecular recognition.